We can prove this very easily using the following identity. If we split up this integral along the right into the two parts, this and this, and we describe the limits over the integrals, we end up with an expression given by here, which equals the improper integral defined in equation 2 here. As long as these two limits exist. Okay? The last two limits are the same as the limits on the right in the equation 2 here. So the statement, we can see that the statement holds if integral 2 converges, its Cauchy principal value 3 exists, and furthermore the value is the number to which integral 2 converges. Next, we check some cases, the interesting cases. The Cauchy principal value of an integral exists even when the integral diverges. That is, it is not always true that integral 2 converges when its Cauchy principal value exists. Okay, so we must be careful. Let's take for example for this. Okay, here we consider the integral of x over an infinite interval here. If we find the improper integral using equation 2 here, the first we check the second part here. The first term will approach negative infinity because this the antiderivative of this function x is x squared divided by 2. So this will result the negative infinity, and this second part will approach positive infinity because the antiderivative of this function x is x squared divided by 2, and we consider the interval from 0 to R2, and we describe the limits as R2 approaches the limit. We get this, which is positive infinity. So the sum of negative infinity and the positive infinity is undefined, which means this integral would diverge. However, we find the Cauchy principal value here of the integral using equation 3, this definition. The answer comes out to 0. So we see that the Cauchy principal value exists even though the improper integral itself diverges. Like, given this. This is an example for this statement. Now, we have some observation that we are going to prove here. Before, we are going to study how to use the residue theorem to evaluate improper integrals. The observation concerns even functions which is defined by this property. F of negative x is equal to fx for all x. Okay, we consider the domain of fx is the whole interval, and we assume that the Cauchy principal value exists. The observation concerns even functions, and it says that if f of x here, f of x is an even function, this function, and its Cauchy principal value of the integral of f of x from negative infinity to infinity exists by assumption here, then improper integral itself converges and equals to Cauchy principal value. So for even functions, the Cauchy principal value is equal to the improper integral as long as the Cauchy principal value exists. To check it, first we suppose that fx is defined over negative infinity, from negative infinity to infinity. Because of f of x is even, its integral from negative r1 to 0 equals half the integral from negative capital R1 to capital R1, just because of the symmetry inherent in an even function. An even function is where f of x equals f of negative x. We just checked it. In other words, that function reflects evenly about the x-axis. Similarly, the integral from 0 to capital R2 equals half the integral from negative R2 to R2, because the given function f of x is even. Okay. Now, when we add these two terms, two equations here, what we'll end up with, if we take the limit both sides as R1 and R2 approach infinity, we'll find that the left hand side matches the definition of the improper integral in equation 2. This part, when you consider the limits, which is the definition of this given in the expression 2. This part equals 2 halves of the principal value added together. Okay? And since we know that the principal value exists by assumption here, the left hand side or improper integral must also exist because the left and right are equal to each other. And as a result, we can conclude that the improper integral indeed equals the principal value, here, when f of x even. Okay, this. Moreover, if we just take the second equation, which means this part, second equation, only in R2 and let R2 approach infinity, then we'll find that the improper integral over a semi-infinite interval from R at 0 to R of a given function, even function here equals a half the principal value here if the principal value exists.